I have known Sam for 51 years now. It was the 1962 summer, Steenrod visiting Mexico. He gave a course. Homology of cell complexes. We were sitting at Steenrod's course, and suddenly two very special characters came into the room, which I have never met. That was 1962. Adam and Git. So it's 51 years now. That was 1962. In the last 50 years that we have been friends. But it's only really in the last 50 years that we have been friends. And the amazing thing is that being both topologists, and the amazing thing is last 5 years that we have topologists interacted. It's only in the last 5 years that we have. I've talked with him many times, really strong. And I've talked with him many times. Little questions. And, those little questions. There are tiny little questions. Don't let you go. Those don't let you learn. That, and I would ask him. Don't let you go. Say, yes, it's don't let you learn. And I would ask him, and he would say, yes, I remember because of this. Very well. It's forgotten, surely. He said 3 words, and I remember. Finally understood after. He said 3 words, and I finally understood after trying to learn. Maybe months of trying to learn. I'll say more about Sam in the following. Okay, so there'll be 3 parts. I'll speak of intersections of quadrics that have been mentioned a little bit here, but I want to give an overview. Then about the projective moment angle complexes and the topology of some of them, in case of manifolds. Okay, so what I have been doing during the last years has been solving second-degree equations. That's something very useful when somebody asks you, what did you do? I solved second-degree equations. Okay, very good. Yes. I understand what you do. No, nothing. Studying second-degree equations. Okay. So, what do I study? Let me put it this way. Take a function from Rn to Rk, where f is a quadratic form. So each component is like this. One should have another index going from 1 to k, but I don't want to tensorize too much the notation. And then I'm interested in the inverse image of 0. And of course, to study that, it's very important to study the intersection with unit sphere. And then sometimes I'm interested not in the inverse image of 0, but the inverse image of a point. And then are very many variations on this subject where you take projective Persons, I'll talk about them, and semi-algebraic varieties, geometric structures, many related things. Well, the main ones are when all the quadratic forms are diagonalized. If they are all diagonal, then it's a lot easier to understand what happens. And this is mainly because, as has been said, in that case, the manifold, which is the intersection with all these equations equal to 0 and the unit sphere, then it's a manifold with a quotient at convex polytope. This quotient determines completely the manifold and the action. There's a technical question here about both facets, but I won't go into it. And in other language, this is called universal cover of P, or the generalized moment angle complex with spaces D1, S0. And another special case is when you change the variable in each of the quadrics. You change your xy by zi square. And then in that case, you have an action of the torus. You have the ith component multiplying the ith component of u, an element of here, multiplying the ci, gives you another element of the same space, intersect with the unit sphere, and you take the quotient, it's the same polytope as before, and that's known now as the moment angle manifold associated to the polytope P, or the D2S1 generalized moment angle complex associated with that was Alberto's fault. The first question that I was asked was the diagonal ones. Actually, the diagonal complex ones. These ones. There was a question raised by Camacho Kuiper Palis in their work on holomorphic linear differential equations, and there was a question about in that case they had two equations like this, and they asked about the topology. So we had this seminar, January 1984, Instituto de Matemáticas. Alberto was sitting here, was standing here, and I was sitting there, and he said, there's this question about the topology of these manifolds, and you're going to solve it. Recently, he confessed that he expected that next week I would have an answer. It took me about a year to have some kind of answer, another year maybe to get all the epsilons on the deltas, and I'm still working on that. I still don't know everything about it. Okay, so I started by studying this, and this will be the subject of our talk most of the time. Okay, anyway. And so I'll say very briefly what's the state of the art respect to this. Things I have done with the help of some friends, Sam, Vinicio, Alberto, Yadira. And if I'm speaking about the real quadrics now, and the story is that for two quadrics, or when the number of quadrics is 2, or when the number of, or when the dimension of the variety is 2, we know everything now, in the generic case, of course. And together, no, 2 quadrics plus the sphere, and in that case, we know everything in that situation. When you have more than 2 quadrics, the things becomes terribly complicated, and that's because of the polytope. The polytope helps in one case, but on the other hand, there are too many polytopes. They are not having. Nobody has idea how to classify them, and it looks impossible to have a complete answer for three or more quadrics. Nevertheless, in working with Sam, we obtained many examples with 3 or more quadrics. In fact, we obtained an infinite number of infinite families for which we can tell the topology. There are many other cases where we don't know, of course, and in a certain sense, there are most of the cases we have solved. The people in polytope theory have this feeling, and there are estimates that those feelings are based on, saying that I won't tell you what they are all neighborly polytopes are most polytopes. And we have solved the question for all the neighborly polytopes, and for each neighborly polytope, an infinite family coming from them. So it's a good number. It seems that it's a good number. Here's a picture that to show you that. This here I put number of quadrants, and here I put the dimension of the space. And when you have the dimension of the manifold, when the dimension is at most 2, or when the number of quadrants is at most 2, we know everything now. Generic case, always I'm speaking of generic case. And then for both things greater than 3, then we have these infinite families stemming from certain points to get the infinite families, and there are more and more and more infinite families all the time. In the diagonal case, we have almost the same, but we have some problems. Here's the picture in this case. Together with Vinicio Gomez Gutierrez, we found all the things with at most two quadrics, even they're not diagonal. For all the cases with 2 equations, we'll still have some doubts. The thing is that it seems impossible to be able to decide if I give you 17 variables and 14 equations plus the sphere, which is it's question of the genus only, of course, but it seems very difficult to decide it in every case. What we're hoping is to decide which genera we get. Okay. And many of these results happened in the last 5 years, and it's a consequence of discussions with Sam. I wish I had decided to give a talk about this work with Sam or related to Sam, but then I had the strange idea that I should give something new here for Sam. Not because Sam has heard all these things many times. Let us see what happens. Okay. So what I'm going to try to explain is this idea of projective moment angle complexes. I put the first steps in the title, but then I thought, finally I thought it would be misleading. It would give you the idea that we're beginning, and now there are some things done. A certain part we did a little bit, and it remained there for some years. That's what I've been trying to work, but there are many old things. So you take these quadrics, the complex ones, and consider the action on Cn, scalar or diagonal multiplication, and I will call this projective moment angle manifold. I learned this recently that they're called partial quotients. They're one of the many partial quotients when you divide by a certain product, a certain torus that is not the whole torus, but acts freely. Okay? So I call them projective moment angle manifolds. And we started looking at this with Alberto in 1993, following some work by Loeb and Nicolau that should also be mentioned in every one of these talks. And we worked the case of 2 quadrics, the complex type, and we took the quotient, and the main work consisted in giving a complex structure to those manifolds. The complex structures together with a natural family of deformations. It's not a question of getting the complex structure and then finding the deformations. This manifold they're born already with a huge space of deformations. And then soon later, Merseman started working with Alberto in his thesis, and he showed that most of the, okay, so we were interested mostly in the complex structure, but we knew a little bit out of the topology. And then Merseman came a couple of years later, and he proved most of the things for any number of quadrics, okay? And he added something very important, yet very simple, is that the moment-angle manifolds, that is, the manifolds themselves before being quotient by the action of S1, the old moment-angle manifolds, they weren't called that way in that time. They are also projective. And here's a simple proof. Take a manifold. This is a moment-angle manifold. This one is 2. The product of 2 of those is a moment-angle manifold. When you divide by the action of S1, you just cancel the S1s, and you get the old C is it's a projective moment-angle manifolds. Very good. Yes. But it's diagonal, but in those cases you can always blame all the action on S1. If you have the group here, it's action on both, but with a small change of coordinates, you make it all act on it S1, and then it's just a question of cancel. So every moment angle manifold is also a projective moment angle. Hmm? Okay. And he constructed these complex structures, but went and he up to there it was more like generalizing what we had done, but then he started getting a lot of speed, and he produced. Polytopic, yes. Okay, well. Oh, okay. We have to make a. We need a conference just to unify the terminology. What's a moment angle manifold? What is? No, I'm calling moment angle manifolds to the polytopic ones. That's yes. That's what I read in your book. No? Okay, fine. Forget it. Okay. So here's the brief list of all the things that Merseman did in his thesis, and I won't go into them, but here's many things he did. Okay, and what we knew about the topology, we did it for case 2, and Merseman said, "Oh, he didn't even wrote a proof." He said it's the same proof, and it's the fact that this manifold is 2D minus 2 connected, where D is a certain integer. I will tell you later, but it is characterized by the following fact: you take the quotient here, the projection from the manifold to the projective one, which is a S1 bundle that maps into this big, all these leaves lives in this projective space, but then what we show is that that inclusion could be pushed into a sub-complex projective space of this dimension, and then also that bundle could be moved into here. If I have time, I'll give a proof in a more general setting. Z is a manifold, yes. What? Yes. Okay, it's impossible in the other way. A sphere times another manifold. It's a moment angle, polytopic moment angle manifold. Take a bundle over the sphere with a section. Take a bundle over the sphere with a section. You have a section, and then you project, you get back the sphere. It's a deformation of the map into this subspace. I'll prove it. I'll prove it. I can have a manifold that projects to a sphere. Okay, I'll try to prove it if I have time. Okay, something that's implied by this diagram is that you get in a very geometrical way the height of the Euler class of the bundle. Okay, e to the d is 0 because the bundle comes from a bundle over CP1, CPD minus 1, and it's not, the D1 is not 0 because goes to the bundle over CP1 again. So, and that's what showed that most of these manifolds are not symplectic. Okay, and it also follows that there's a splitting of the homology, one generated by the powers of E and the rest. And then you can have another splitting where you take all the powers of D that come from CPD and all the Poincare duals, and you get a space whose homology looks like that. I meant to prove that later. I can prove it now. I can prove it now if you prefer. Okay. Yes. There are some maps. Right? Okay. And we also knew that this manifold P of C is always a boundary. And how we constructed the boundary? Well, you have all the equations of Z. You turn one of the equations into an inequality, and you get a bigger manifold whose boundary is I call P of C prime plus. That's today's notation. And we have get a manifold whose boundary is P of Z. And then the diagram above is true for PC prime, and then we get everything again. And we get an embedding of CPD minus 1 into PC prime and into PC, PZ. Okay, so that's what. And from that we had the following idea. what I had done before for the moment angle manifolds upstairs was to construct a manifold whose boundary was Z, and it's easier to understand this manifold. What I showed in those cases where it happens is that all the homology of this manifold with boundary, it's given by spheres, and then it follows easily that from H-cobordism theorem that then the manifold is a connected sum of products of spheres. So something similar we did for this, and we tried just one case, or collection of cases. We take the ones where the coefficients are the 2L plus 1 groups of unity, and we showed by this method that this manifold is a certain sphere bundle over CPL minus 1 plus a connected sum of products of spheres. Okay? And this kind of product appears also in the theory of complex complete intersections. It's not a product, it's twisted product, it's a bundle. Just I want. Okay? And this type of manifolds appears also in the work of Bill, Lipgover, and John Wood, and they were studied by Sam with, have some trouble here, and some friends. No, not for us. For Bill, there's an ARF invariant, and I don't know for the others. So I wish there was a name for this kind of manifolds. That's a job for Bill. We need a name for those manifolds. It's we have very particular equations with this, and the polytopes are determine the polytope. I cannot tell you. I cannot write for you the polytope. There are two quadrics, so these are complex numbers. Okay. So do you have a number for this? Name for this? Bill? You're thinking of a number, a name for this kind of manifolds? Okay. Before somebody calls them BLW manifolds. Hurry up. Okay. So we got these guys. These are the simplest cases from our point of view. And we stopped there. And for this occasion, I meant to go back to that problem and finish it. Okay. I just said that Sam worked on this too, but I'm not an expert on these complete intersections. I just try to look at the manifolds they get, see what they are. Then the easiest case is when the polytope is a product of simplices, and then the manifold is a product of spheres, and we get when we take the quotient, we have something that we might call a projective product space complex, similar to one studied by in the case of the real case by Don. Okay, and so this work by Don has some relation, and very recently, after I sent the abstract, I discovered in the book by Taras and Victor the following formula for the cohomology ring of P of C. Here it is. I wish I knew how to use this formula. I don't know how to use this formula. And one curious thing is that from that formula, they derived the same result about the height of the Euler class. So I wish I could know that. So I'm giving problems after each section. Here, problem 1 is study the theory of complex projective product spaces. That's a problem for Don, but I hear Don is doing some very important things in other fields. So it's open. So it's open. Anyone can take this. Or anyone in this room. This should be a lot simpler than what Don did. S1 is simpler than C2. And the other problem is to understand the Buchstaber-Banach Tor formula. That's a problem for me. I should have tried to understand what it says. That's a problem for me. That's a problem for Sam. With the help of Sam. Okay. Okay. Let's move on. So all this was about intersections of quadrics. Okay? Now I part to second part, the projective moment angle complexes. So the story here is that many of you have heard it, but some of you haven't. And it's a very nice story how I came into the moment angle complexes. Forget for the moment about the projective. About 5 years ago, I went to a talk by Sam about moment angle complexes, generalized moment. I didn't know what it was. Went to the talk. I sat there. I didn't understand a word. I had got no idea of what the moment angle complexes were, but somewhere they were very familiar. This was something very familiar. There was a complex there that was organizing all the topology. There were some splittings. All the things that had gone in the previous year were going on there, but I couldn't understand. I have an image that I was like in a dream. In a dream, I was sitting in my house, in a table full of people. These people were quarreling, being friendly, all kinds of relations between them, which were identical to the relations between members of my family. But I couldn't recognize any one of them. None of them was a member of my family. So I was sitting there in that dream. After a number of sessions at Dr. Gittler's couch, I discovered that they were really my family. It was really my family. It was just disguised in a certain way. I say family, okay. Okay, so we worked. I started working with Sam, and we got I learned a lot, and then we passed to solve on other problems, and Those are what I already told about. Okay, so let me see if I learned something from Sam. So I try to do the projective thing for a simplicial complex. Okay, and here's my definition of simplicial of moment angle complex. One line. Well, it's a long line, but it's one line. I have a paper with the proof that it's the same definition, but it's more or less obvious. The moment angle complex on a simplicial complex is a subset of those points in d2 to the m seen as part of complex space of dimension n, the set of those collections such that the set for a point is there if the set of I is such that Ci is less than 1, or that Ci is not in S1 is a simplex. I'm not claiming it's original or whatever, and that's my definition, and I'll use it right away, and then you can take the quotient. And I'm assuming that K is not the full simplex on M. Okay, then you can do practically all the same things. First of all, you have the whole thing, the whole set of vertices is not a simplex. That means that 0 is not an element of C of K, and then you can push it to the boundary of the sphere. And also you cannot have any points that where all the points are inside the disk, so you cannot have real positive multiple points. So this is actually an embedding. So you can embed this here. So that gives me possibility of equivariantly, yes. And in this case, we have the same diagram as before. Let me try to prove it now. Okay, if you have a collection of vertices that is not a simplex, then that means that that collection of variables, the corresponding collection of variables, cannot be all 0. So that means that our space doesn't intersect the subspace given by those variables equals to 0. Okay? I'm proving it. I'm going to define it right now. D is the, I'll tell you what it is now with the proof. Okay, I was saying take in the polytope, take a collection of vertices that is not a simplex. Collection of vertices that's not a simplex. That means that that collection of, the corresponding collection of variables cannot be all 0. Okay? So that means that my manifold up here and down here doesn't intersect the subspace where all those variables are 0. That means that I can push my manifold to the complementary big sphere or subprojective space. I can push it the other way. Of course, the less equations I have, the bigger is my space, the bigger is the complementary space. So I take the smallest collection of variables where you have a non-simplex. That I call that D, and then this projects. Then I can push the inclusion of this. I can push it into a CP D minus 1. Okay. And then on this side, it turns out, you know that I cannot prove it right now, that in this case, this manifold is 2D minus 2 connected. Okay, if Z of k is 2D minus 2 connected, then this bundle is a universal bundle for spaces of dimension less than 2D minus 2. So there's a bundle map here. So that's how those are the maps, and that's how you embed the inclusion of this bundle in this. And of course, the bottom line gives a classifying map for this, so it's inclusion. Yeah. Finish. It's proved. And again, you get the height of the Euler class from this, which is d minus 1, etc. And there's a splitting, etc. So there's a splitting, but a partial splitting. So I have, again, more problems than results. So here are some problems. Find a complete splitting of the projective manifold. Recall that for the suspensions of Z of k and the projective product spaces of Davis, there are these complete splittings. So it's natural to think that there's a complete splitting for the projective one. And one wonders if the Buchstaber-Panel formula is also true. Taras told me it should work equally well. And for any, okay. The book's for manifolds, but it should work for any complex. And what I did here for quotients by S1 should be done for more general moment angle complexes. Into stunted projective spaces. I asked Don if he had an analog, and he said, no, I don't have one. Okay. Sure, I hope. So it's okay. So it's okay? No. But okay. What's that? Okay. Okay, let me go. I'll have still got to arrive to the main part of my talk. And we can remember when in the manifold case, we constructed a cobordism, a manifold whose boundary is the projective. And that we can mimic with generalized moment angle complexes. You have to substitute the pair D2S1 in one of the vertices by D3S2. If you have that, you get a complex, which in the case of the manifold is the cobordism we did before. Question, what does it mean? I said that the manifold PZ is always a boundary. Yeah, and I showed how to do it. You just change one of the equations by an inequality. There's a different equivalent construction coming from things we know now, and that can be mimicked like this with a moment angle complex. What does that mean? In the manifold case, the dimension is good enough so that you can change the map into ZK from the complex into a inclusion, embedding. Can you do that with a complex? I mean, we know that not all complexes are manifolds, but how bad can they be? how much do you have room for doing general position tricks and getting embeddings and things like that. And, well, what can you say about it? Okay, so now we're getting to the best part of my talk. We had seen the topology of the manifold, of the projective manifold, when we had the powers of 2L plus 1 root of unity as coefficients. Now we take the equations, but each of these powers we include it in ni times. So we take this with multiplicity ni. So we get this number of variables. Total number is n, and it's a result from back in '84 that any case with two quadrics, you can put it in this normal form. I have an anecdote about that. I got that when I was visiting IHES, thanks to Dennis. And one day I was at home when I discovered this, and I immediately phoned Dennis. You don't remember. Of course you don't remember. 1984, almost 30 years ago. And I remember talking to him on the phone booth. It's all about partitions. I discovered it's all about partitions. I'm sure he couldn't understand anything. I haven't told him what I was talking about before. It's all about partitions. Yes, I got all the partitions. Okay, but I'm sure. Oh, okay, you remember. Okay, so the thing is that main thing here is that everything is given by the partition. From there you can derive everything about the topology. And then we have to describe the topology of P of C for L. For L equals 1, it's the product of the spheres. For L to be greater than 1 is the case where Z is a connected sum of products of spheres. So you get the Giesen sequence, you have the Giesen sequence, you have an embedded CPD minus 1, we're talking about manifolds now, and you had this, the homology of PC now looks like this. You have the homology of the CP D minus 1, so you have the powers of the Euler class. Then you have in the middle here other classes, homology classes, and up here you have a class Y and the products of Y, so y e to the d minus 1, which are the Poincare duals here. So you have like a CPD minus 1 cross the sphere, whatever the dimension, and on the other hand you have all these classes. You have that splitting. And from there on I wanted to work and see that I had this sphere bundle as a summand, direct summand, and then all these classes giving the products of the spheres. That's and that's what we knew. And we knew it worked for the case where all the coefficients were simple. And other cases I tried, so I had this optimistic conjecture. For two equations and L plus 1, you always get a Bill-Browder manifold. No, maybe I don't call it Bill-Browder manifold. You'll get that kind of manifold, connected sum. You might think it's too optimistic, but the thing with this subject is that I've had 4 or 5 optimistic conjectures that I've proved in the last years, thanks to my old bag of tricks and the ideas that I learned from Sam. And, well, I tried to work on that. how, there's this other conjecture closely related. The closely related conjecture says that for all these intermediate classes, the power with the Euler, the product with the Euler class is 0. That's equivalent to saying that from the Giesen sequence that all these classes come from above, from the total space of the bundle. So they are spherical, and there's some problem because sometimes they will be too big in dimension, but that's something I don't worry too much about. I've been able to deal with that. So the main part is proving this conjecture. And I worked and I worked and I worked hard proving that conjecture. I worked hard with the deadline of the 25th of September, getting closer and closer, and then I discovered it was not true. There goes your present. Okay, here's the example. In the notation before, you take this manifold is Z, so D is 4, here we know it is 4, and then it turns out that that means that this goes up to 3, so I have two intermediate classes, and the cup product between them is non-zero. It's an isomorphism. They're not, so the conjecture is false. I'm trying. You will help me. Okay, there's the cohomology of this. Have you seen it? Anyone has seen that cohomology? Please, can you read those little numbers? Can you read them? You cannot read them? Yeah, but can you see it? If you cannot see it, let me get it bigger. So it's big. I'm not including E2, E, and 1, but so I have the powers of E times this, and then these two intermediate. And, well, the Poincaré pairing, you can assume that it's a symplectic basis, so that you have that. Please, someone has seen that manifold? An H space, maybe? Well, that's my search. I'm looking for that manifold. I hope somebody in the audience helps me. This looks... What? Okay, you'll tell me later. Anyway... Yeah, I'm afraid so, but I'm optimistic. Why am I optimistic? I got stuck like this once before. 1984, I was looking for a manifold of dimension 7 simply connected with the free action of the 5 torus. And I looked and I looked and I looked and I found it. That's it. Now we know it is. Now everybody knows it is, but at that moment it was a miracle I found it. The work of Dennis McCaffrey. So that's why I'm optimistic. I got stuck here in the same way. I hope there's another way of saying what it is. Plumbing, twisting, connected sums, etc. Okay. So the counterexample generalizes. There's an infinite number of counterexamples. We have also an infinite number of counterexamples for which examples for which the conjecture is true. And here's that case we get one of these manifolds when you get 4 ones and another integer. And so we have new problems. When is the conjecture true? When it's false? It's very tricky because if you have a gap in between you have no gap between the intermediate classes, then there's no room to have products by E from the Gissen sequence. But if it's too big, then you cannot have products with E, non-zero products with E, because once you get to the E to the D, then it must be zero. So you cannot have those isomorphisms. So it's very, very tricky question. The cohomology ring is that these intermediate classes, well-defined intermediate classes, the cup product of the Euler class with these classes is zero. That's a conjecture, and it's false. Okay? And I have some more problems there. I hope for a simple construction or description of all the cases. And for more than K, Sam and I found many cases. And in particular, one of the things we solved was this Bosio-Messermann conjecture. And now there could be this same conjecture for the projective ones. And all constructions, problems, and difficulties should be the same for the real case when you take intersection of real projective quadrics. Okay? I haven't done the details, but it should be very similar. So here's my description of the state of the art. Before, for the manifolds, we had all this thing in blue, meaning we have solved all the cases. Now we have some cases we know, infinitely many. Some cases we know that it's false, and many other cases we don't know. Remember, I'm doing the real case now, so there's no trouble with the two-dimensional ones. And here we have all the cases we proved with Sam. They'll still there. Of course, they are the trivial ones, the ones for which Z is PC times S1. That's the zero, D equals zero case. The conjecture is true for those, okay? That's what Sam and I proved. So that's what I have. I tried that. I tried several other things, old and new. I tried all my tricks, and it seems like Murphy's law case. Everything seems to go wrong, but well, that's a challenge. My present for you is not as beautiful as I hoped. I hope a complete answer in this case. Sorry, Sam. But I know you like problems. I have plenty of problems for you. Okay, so there's much work to do. My old bag of tricks, enhanced by the contact with Sam, is not working now. So I need to talk more with Sam to see if we can get more of this. Thank you. Question? Oh, I forgot to. In RE4, in dimension 9 and I get it right here. In dimension 7 and 9, there it's a free group on 4 generators, which I call AJ. 4. In the factorings, when one of the 5 above becomes a 4, so we have 4 here and 4 here, and there's we have this base and this base, and these are Poincare duals. The product to AJ, AK should fall in here 7 times. No, something's wrong. I have something wrong here. Yeah. No, it's there's a mistake here. This should be E3Y, yes? 7, 9, they're Poincare duals. Their product should be in the top class. This should be a 3. Okay? One. I write here the Betty number 0, 1, 0, 1, and that's dimension 0, 1, 2, 3, 4, 0, 1, 5, 6. Generators 1, E square, E cube. Then in dimension 7 I have AIs. Dimension 8 I have nothing. And in dimension 9 I have the multiples of this by 8 I. And then now I have this in dimension y, ey, e squared y, e cubed y. No, it's okay. The product of the EIs should be a square e squared y. Previous. Yes. I would like to know a different construction, simple construction. Yes. I want to tell everybody so everybody understands which manifold it is. No. When in the analog. That's the pessimistic conjecture. Yes. I wonder about.
Can we continue this later? Maybe we have to continue with the next speaker.
No. When I have what. CP3. Let's thank the speaker again.
The speaker is asking me to please move on and and let please give a thank you very much to the speaker. So so we're going to have our next speaker next.